Who jumps out of perfectly good airplanes in the name of science? Mr. C.
And a wonderful Tuesday to all of you 8th graders out there, and a wonderful Tuesday it is. Mr. C, that's your opinion. No, it's going to be a great Tuesday. And one of the reasons it's going to be a great Tuesday is I'm going to tell you now what's on the test. Okay? So, and what to triple R, and then I'm going to review a bunch of things with you, and it's going to be all good. So, anyway, but I think I used the figure of speech already with you. You can lead a horse to water, but you can't make him drink. You can tell an 8th grader what's on his science test, but you can't make him triple R. You gotta want it. It's up to you. You can easily get an A or B on this test. And I think Mr. Phillip maybe even, said something to you on Monday that will enhance the probability that you could get an A or B. So anyway, you ought to get an A or B on this. You really should. So, but like I say, you can know what to study, but you've got to go over it. Okay. I'm pretty sure Mr. Phillip handed this out to you in class. You have your own copy now. And you're going to triple R it. What do we have to study? All of this top section on chemistry, study it. I've added density over there on the side. Do you see it? Density. Are you scrambling to write density right now? You should be. Density, atomic packing, how tight the atoms are packed. So study that top section. Then study the standard model of physics, the two kinds of particles, the two groups of subatomic particles, sub under atomic, atom, under the size of atoms. There's the neutrons and the protons. What are they called? Quarks. So there's those. So neutrons and protons. You know how it just strikes me. I would have learned it this way. So why didn't I teach you this? So if neutrons and protons are quarks, you could go in the alphabet P, and what follows P in the alphabet? LMNOP, Q. Quarks. P, protons, followed by Q, quarks. So neutrons and protons are in the category of quarks. Hey, thanks for that tip, Mr. C. No charge. So anyway, why didn't I see that before? So anyway, a little brain glue. I hope you remember. P, protons are in the quark category. And then you've got electrons, and they're in the lepton category, along with neutrinos. So the standard model stuff. And then next, right down here, the 4 fundamental forces. They'll be on the test. Can you rattle them off? Gravity. Do you mean gravity? Of course. Gravity, the electromagnetic force, electromagnetic attraction, opposite charges attract, like charges repel, opposites attract, like electrical charges repel, push away. Are you paying attention? Are you listening still? Are you taking notes? Okay. So, and then the additional 2 fundamental forces. The strong force that holds the protons together, that overcomes that repulsion force, strong force, and the weak force. And then the Higgs field stuff. The Higgs field and the very mysterious Higgs boson. So, and it's the Higgs boson particle which gives particles their MASS, mass. Right there. You're going to ask that again? Yeah, I asked it the last time. There it is, right there. And then you've got the standard model particles, have precise mathematical values. If you've got precision, you've got someone who is a precisioner, I'll call it. If you've got precision, it couldn't be random, it couldn't be an accident. Evolutionists like to say, oh yeah, it's just an accident. Right. No way. That there is, can I tell you guys are smart 8th graders, right? Can I tell you about Occam's razor? Huh? Occam's razor. It is a principle of logic. Here's the way it works. So if you see design, is it logical then that it formed all by itself? If you've got architecture, if you've got artwork, if you've got an invention, is it logical, the next thing to say about that it all formed by itself? No. Occam's razor says this. If you have a couple of hypotheses, which one do you go with? The one that's the simplest, that makes the most sense. That's called Occam's razor, named after an Englishman back in the late 1200s, after the Magna Carta was signed. Anyway, he's a smart guy. He just said, hey, if you've got two possible ways to explain a hypothesis, go with the one that makes the most sense, the simplest of the two. That's Occam's razor. That would be a great bonus point, wouldn't it? OCCAMS, razor. Occam's razor. Go with a simple, logical explanation. And that's what creation is. You've got design. What is the logical explanation? A designer. So you've got stuff that's been created. You've got a creator. You've got specificity. You've got a creator who designed and created with specificity. So anyway, that's standard model stuff. And then over here on the back, no foam and pillars. Nope, nope, nope. No gray whale stuff. Nope, nope, nope. So, and no 7th grade stuff down below. That's not for you. That's not for you. That's geology for the 7th grade. But the verse stuff is for you and for them. Hey, I'm going to have you write John 1:3 again. John 1:3? Hey, Mr. C, did you know I still haven't learned it yet? Yeah, I can see that. I ask it almost every test or every other test. And a few people, a handful of people, don't know it yet. It's going to be worth 2 points, this Thursday's test. So I'm going to make you pay if you don't learn it. All things were made by him, and without him nothing was made that has been made. John 1:3. So 2-pointer there. Colossians 1:17. See that? I'm going to ask you again, what does it say? It says in Jesus, it's speaking about Jesus, in him all things hold together. I'm going to ask you for those 2 words. What does it say about Jesus and the universe or atoms, all matter? Because of Jesus, in him all things hold together. The universe holds together. Could he be using gravity to cause that to happen? Sure, of course. But we don't know all the reasons behind it. Okay, how are we doing time-wise? Good. Okay. You know that I'm going to ask you a number of questions from LS8, which I've already gone over yesterday. LS8. Triple R it. Vertical groups, families or groups, horizontal ones on the PTE, periodic table of the elements, periods. Hey, when I ask you this, I'll take off half if you put down PTE as your answer. What's the smallest part of an atom? You're not going to say PTE. The PTE is this chart that just shows all the different kinds of atoms or elements. But when I ask you what's the smallest part of an element, you're going to say atom. But the other thing is, what are the 100 or so building blocks called? They're called elements. I want one word. Elements. Back to that in a minute. So there's LS8. LS9. Went over it yesterday. Metals. What are all metals like? Great conductors of heat and great conductors of electricity. They're shiny, they have luster. You can beat them into sheets. That's malleable, like this. A copper sheet. It's been beaten. So metals are malleable. Metals are malleable. Trying to give you some brain glue. Say it to yourself. Don't say it out loud. Metals are malleable. You beat them into sheets. Okay. Metals will corrode. They'll combine with oxygen or other gases and get weaker. And then on the left side of the periodic table of elements are the alkali metals. I didn't write it down here on this one. So above family number 1, alkali metals. I'm going to ask you for 1 or 2 examples. So what are you going to give me? You've got lithium, sodium, potassium, rubidium, cesium, francium. Just an example of an alkali metal. Okay? So you know I'm going to ask you metals on the left, metalloids in the middle, and nonmetals on the right. Metals, metalloids, and over on the left, nonmetals. Metals, metalloids, nonmetals. Okay? So anyway, all of that. What are man-made or synthetic elements called? Transuranium, because they're beyond uranium, which is 92 on the periodic table. So if I say to you, I'm not going to ask you to remember transuranium, but if I put down, hey, explain what transuranium elements are. Those are the ones that follow or are after, and you'll say uranium, uranium. Okay, that's LS9. LS10. So you've got it out in front of you, right? LS10. Over on the right, it tells you about nonmetals. What are they like? They're not good conductors of heat and electricity. They tend to be dull and brittle. Nonmetals. And right here, there's a number of families right here of the nonmetals. There's nitrogen and oxygen is there, and hydrogen. Let's see, what other groups? The carbon family. So I'm going to ask you for right there in the second box. And it says, what are the families containing nonmetals? So you're going to give me a couple of those. You're going to study those. Carbon, nitrogen, oxygen. So those. Okay. And then you're going to give me an example of a metalloid. Mr. C, you've got one there, don't you? Maybe. Yeah, I do. Here it is, Si, silicon, right there. Used to make the circuits, the microcircuits in computer chips. silicon, Si. An example of a metalloid. Okay, so that's LS10, and then LS11. I want to focus on it today. It's all about radioactive elements. So you've got LS11 out, and I'm going to show you some pictures of them really quick. Before I do, just a little aside. There is the Perseverance helicopter all ready to fly, but something with the software didn't quite work right, I think yesterday. So now they're going to have it fly on the 14th, I think. So anyway, I'll give you an update on how it does and all of that. So, and I want to show you this. Here it is. Radioactive elements are elements that spontaneously, without any help, they just fly apart. They're not bonded very well, and they fly apart, and then they give off some energy. So this is all on LS11. Here's a nice little diagram of this. Get it right. Radioactive elements. There you see a nucleus of uranium, a kind of uranium. Uranium is one of the radioactive elements. And it spontaneously breaks down and flies apart. What do you get? What flies apart? Well, you get alpha particles, 2 protons and 2 neutrons. You see that? Alpha particles. And you get beta particles, which are electrons. You get neutrons flying out of there. So this is what happens in radioactive decay. Most atoms hold together well, but a few are not real stable and they fly apart fairly easily, like uranium. And then you get alpha, beta particles that fly out, and then gamma rays. So you're highlighting this, right? It's on here, the 3 kinds of particles. In the second box, alpha particles, beta particles, gamma rays are given off when the nuclei of radioactive elements break apart. Now, I've given you 2 that I want you to remember. Do you see them there on the side? U and Ra. U for uranium. What is it, 92? Down there on the bottom, 92. Yep. Number 92, uranium. It's radioactive. I would stick right underneath it Ro. I would put Ro right underneath uranium. Are you doing it? Do you have your periodic table out? Are you working with it, or are you just sitting there picking your nose? So I'm going to ask you this. A lot of stuff on the PTE. Mr. Phillips looking around and going, how are you guys doing with your PTE? Down at the bottom, U for uranium. And then over there on the side, do you see it's number 88, Ra. You see it? For radium. It's another example of a radioactive element that spontaneously flies apart. Just breaks apart and gives off particles. Hey, Mr. C, I have a question. When those particles fly out, what if they would penetrate my body? What would happen? Well, let me show you. I have a little kind of thing to show you. So here it is. An alpha particle barely can penetrate paper And in fact, it's stopped by paper and it's stopped by your skin. Woo! Good news. So whenever a radioactive element decays and the nucleus flies apart, so alpha particles are stopped by really thin things, including your skin. It's good news. Not so lucky with beta particles. Have a look. They can go through paper or through the skin and cause damage to your tissues. Beta particles. And then, oh my, look at gamma rays. Gamma rays, they can go through skin, and then they can go through aluminum. They can be stopped by lead metal. Hey, you know when you go to the dentist, what do you get on you when you're getting x-rays? What do you get? You get a lead sheet, right? Kind of put over you, or lead apron. What's it for? To block the radiation? I didn't know that. Oh yeah. Yeah. So there's some radiation with the x-ray. You know, it's taking a picture of your teeth, your jaw. So, but it's sending particles, it could send stray particles into your cells and cause damage. So, and too much radiation can cause a lot of damage. Cancers, blood cancers, tissue cancers. So, alpha particles, not so dangerous. Beta particles, different story. And gamma rays, really dangerous. And then neutrons can penetrate through lead. So they've got to be stopped by concrete. So you got to be careful with all that stuff. Now I want to show you this. Here's how we use radioactivity. One way we use it, so have a look at this. Some of you have seen this as you've flown into Phoenix. This is about 50 miles west of Phoenix. I think I've seen this, Mr. C. Have you seen this? Everybody have a look at this. Raise your hand if you've seen this from the air coming into Phoenix. Shortly before you land, a few minutes out, you'll see this. You'll usually fly to the south, but out the left window you can see Palo Verde Nuclear Generating Station. Is it a nuclear power plant? Yes. Does it use radioactivity? Yes. Does it use uranium? Yes. Do they let the uranium atoms break apart? Yes. Does it release radiation? Yes. No worries. Here's what they do. They release all of this inside a containment building. Let's see if I can show you this. Think I can. Yeah. Here's the design of Palo Verde Nuclear Generating Station. Do you see the kind of round dome there? It's called the Containment Building. That's where the radioactive uranium is being released. Can you see that? And whenever it's released, it produces energy, a lot of energy. And they use it, and this is what I'm going to ask you on the test. Are you writing? Are you writing? I hope so, on LS11. Down below, they talk about how they use how radioactive elements is useful. See that? It's useful. Look what I have. To make electricity and to diagnose and treat diseases. Are you writing? Down at the bottom on LS11, how do they use radioactivity? To make electricity, to generate electricity, and to diagnose and treat diseases. First, let me explain this. At Palo Verde Generating Station, that containment building is made of thick concrete. Oh, concrete, that's good news. What does concrete do? Remember, it blocks gamma radiation, and all the other kinds. So they don't let it escape. They don't let it out. And they heat up water and make steam, and the steam turns turbines to make electricity. Oh, okay. So it's a radioactive or nuclear generating station where they make electricity. In fact, our Palo Verde generating station is the top nuclear plant in the United States for making electricity. How many different reactors do they have? Well, just look at the containment buildings. How many containment buildings do you see? There's a reactor deep inside each one. How many do you see? Uno, dos, tres. Three. 3 reactors, and they make a lot of electricity, more than any nuclear generating station in the United States. Year after year. What did it say? It says for the 23rd consecutive year, producing more, the largest generator of electricity in the U.S. for the 23rd straight year. Wow, that's pretty cool. And it's very safe. They haven't had an accident where there's been a release of radiation. So, do you remember in Russia, you remember reading about it, you were too young to be alive when it happened. But I don't know, maybe 30 or 40 years ago, there was a nuclear generating station in Russia called Chernobyl. And they had an accidental release of too much radioactivity. What did it do? It killed people in nearby cities or city, and it eventually caused the DNA to mutate in people's tissues and their cells, and people down the road, lots of hundreds of people got cancers. So anyway, well, thanks for that sweet little bit of information. But our nuclear generating station is safe, and they're doing a nice job of making nuclear radiation. I wanted to show you this, and you're going to highlight this on LS11. Down at the bottom, is it down at the bottom? I've got to find this. There it is. In the top box, over on the left side, it mentions Marie Curie. She was French. You see her over there on the left side? Highlight her. Marie Curie. Here she is with her husband. I think his name was Pierre. They were French. She discovered radium, Ra, radium. Remember, these two elements you've got to know. U for uranium and Ra for radium. They're radioactive. Radium is radioactive. Uranium is radioactive. Spontaneously gives off energy, particles, alpha, beta particles, and gamma radiation. So, anyway, what happened, Mr. C, to Marie Curie? Both she and her husband were exposed to too much radiation. They didn't know, because they were experimenting with radium. They didn't know, and she ended up getting I think it was a kind of blood cancer that took her life in 1934. Her husband recovered. So anyway, they were very brave. They were studying elements they really didn't know the properties to. So anyway, okay. Now, one last thing to do. You're going to highlight all these and you're going to study these. These are the ones you've got to know. So highlight them and study them and their little stories. There's the bookend ones, hydrogen and helium. H for hydrogen, He, helium. The two gases found on the sun. Hydrogen is explosive Helium is not. They're both lighter than air. So hydrogen, helium. In the second row, you've got to know carbon found in living tissues. Carbon, C for carbon. And then, of course, N for nitrogen, the major gas in our atmosphere. O2, oxygen, the secondary gas in our atmosphere. And then neon, a gas that gives off light. Ne, neon. A lot of these are easy. Neon, N-E. A lot of these are really easy. All right, in the third row, a light but very strong metal, Ti, titanium. Ti, titanium. And then Fe, iron. Fe, iron. Cu, copper, good carrier of electricity. Al, up above, Al, aluminum. And then Si, silicon. I showed it to you. A poisonous gas, Cl4, chlorine. So Mr. Phillip is going to remind you of each of these. You've got to know the symbol and the little, a couple little factoids about it. And then I've already said Ra, radium, and U, uranium, both radioactive. Radium, radioactive. Uranium, radioactive. You're going to have to give me one example of, over here, these alkali metals. So lithium, sodium, potassium, I don't care which one you give me. Symbol or name. Then we've got silver. I have a silver coin, a little bit of silver in it, if I still got it in my pocket. Silver, Ag. Remember, it's the opposite of gold. Gold's got a G in it. Ag, silver. It's got a little bit of silver in it. Au, gold. Gold is number 79. Silver is 47. Sn for tin. Here's a tin can. SN tin, number 50. And then PB for lead. And I've got a chunk of lead somewhere. Lead metal, remember, it's poisonous. The Romans used it in their water pipes. PB, lead. Okay, I'm going to turn it over to Mr. Phillip. And you are going to make sure you've got all 20. If any of you had any questions, you know what to study. LS 8, 9, 10, 11, and 12. I'll go over 12 tomorrow. And then the PTE, the study guide that was passed out in class. Triple R, my friends. You can lead an 8th grader to the test information, but you can't make him triple R. So are you going to triple R? We'll find out now, won't we, on Thursday? So I hope you will. You ought to get an A or B. Trying to help you out. So care about you, praying for you, love you. See you on Downhill Day. Adios.